Welcome, geometry students. Today we're going to work with the target, which states determine and calculate area of triangles and regular polygons. We're going to focus on the regular polygons today, since we've already learned how to calculate the area of triangles. Okay, so there's some new vocabulary you need to be aware of. As we're talking about this, you do have a picture in the You Try Now. In your annotations, I should say, and I have that in the bottom left corner, so I'll be referencing that as we speak. So the first thing you need to know is the center of a polygon is the point inside the polygon that is equidistant to all vertices. Keep in mind the word equidistant just means equal distance. So basically when we're talking about the center of a polygon over here on the picture, J would be the center point of that particular polygon, in this case an octagon. And the reason why that's the center is that point is the same distance to all vertices A, B, C, D, E, F, G, and H. So that's the center of that polygon. The radius of a polygon. Now normally we hear the word radius when we're dealing with a circle. So today we're going to talk about where the circle comes into play. We'll get to that in a minute. But the radius of a polygon are the lines joining the center of the polygon to each vertex. So we've already said that the center is J, and then the vertices would be A, B, C, D, E, F, and H. K is not a vertex. Please be aware of that. It's just a point on the side. But if we were to draw a segment from A to J, for example, J to B, J to C, and so forth, that's going to be what we call the radius of the polygon. Now keep in mind those should all be the same length because they're all the same distance from that center point. The apothem of a polygon is the perpendicular distance, so it must make a right angle, from the center to any side. So if we look at our picture, the apothem is going to be the perpendicular distance from the center to any side. So here's our center. The apothem is this length here. In this case, it's KJ. So it makes the perpendicular distance. It's also going to bisect that side length. So that's an interesting relationship there as well. So it's going to be a perpendicular bisector. The last definition we need to discuss is central angle of a regular polygon. This is an angle formed by two radii. Radii is just plural for radius. Drawn to consecutive vertices of the polygon. So if we look at a central angle, it's an angle formed by two radii drawn to consecutive vertices of the polygon. What we said before, an example of a radii would be AJ or BJ. So this is the central angle that we're talking about. Take a moment to look through these definitions again, because we are going to be using them throughout the notes, and if you don't understand these, you won't necessarily understand what I'm talking about when I'm referencing them. So please take a moment to pause your video and read through these and make sure you understand what these are all referring to on our picture. All right, let's take a look at example 1. Example 1 says we're going to find angle measures in a regular polygon. Keep in mind, the key to this target is we're dealing with regular figures. So a reminder from last unit, regular figures have to have all equal side lengths and all equal angle measures. So if it doesn't fall into fulfilling both of those requirements, we're not going to be able to calculate the areas and so forth like we will be today. So today has to require regular figures. In the diagram, ABCDEF is a regular hexagon. So automatically we know all 6 sides are equal and all angles are equal. It also talks about a circle G. So this notation here we haven't seen before. That's telling us that circle G is a center point of that circle. Find each angle measure. So we're given 3 angle measures we need to find. Now before we discuss the word radius of a polygon, and I said, well, normally that works with circles, not polygons. But if you look at this, the polygon, in this case a hexagon, shares the center with a circle. So essentially, this segment GE is not only a segment that's part of our polygon, it's also the radius of a circle. So when we talk about a radius, it's because we're putting our polygon with all of its vertices on a circle. We call that a circumscribed circle and an inscribed polygon. Essentially, the polygon is inside the circle and the circle's on the outside. We call that, again, circumscribed. Okay, so let's move on to finding angle EGF. So angle EGF is this angle here. That's what we referenced as a central angle of the polygon above in our notes. So what we want to consider is that this hexagon essentially is broken up into 1, 2, 3, 4, 5, 6 triangles if we were to draw in the radius of the polygon. So we have 6 congruent triangles since this is a regular figure. Now what we need to consider is what would each of those central angles be? Well, if we consider that these are the 6 central angles we're discussing, all of those are going to form a circle. So the total for that around the center would be 360 degrees. So we can find the measure of angle EGF by doing the total, which will always be 360 degrees, divided by how many central angles there are. In this case, there are 6 central angles. Keep in mind, this central angle number will equal the number of sides. So if we were dealing with an octagon here, we would do 360 divided by 6. Well, if you do if we're dealing with an octagon, we would do 360 divided by 8. In this case, we're doing 360 divided by 6 since it's a hexagon. So each one of those figures is 60 degrees. And that's totaling to be the circle. The next we have is angle EGH. I'm going to go ahead and erase my picture just so that we can start fresh. So angle EGH. Here's angle EGH. Well, we just calculated this whole angle to be 60 degrees. If you recall, we called this segment GH, we called it the apothem. The apothem is the perpendicular distance from the center to the side. So in this case, the side is FE. Now I also commented that the apothem is going to bisect the side length. So when we look at this, that's also going to end up bisecting the angle. So if the original angle is 60 degrees, that's going to divide each of these angles into 2 equal parts. So each of those would be 30 degrees. So angle EGH is equal to the central angle divided by 2. So essentially the apothem is a perpendicular bisector, and it also bisects the central angle. Next says to find the measure of angle HEG. I'm again going to just erase my picture. So HEG is this angle here. Well, if you notice, we just calculated this angle to be 30 degrees. We know that this is a right angle because the apothem must be perpendicular to the side length. So really all we're doing is using the fact that the 3 angles in a triangle add to be 180. So we're taking away the 90-degree angle. We're focused on this triangle, by the way. We're taking away the 90-degree angle and the 30-degree angle, and that leaves us with angle HEG being 60 degrees. Now we're going to use these different angle measures a lot throughout this particular target. So please take a minute to make sure you understand how I calculated these three angles. Alright, let's look at the formula we're going to be using today. This is the area of a regular polygon. Up until now, all of our formulas were specific for maybe a parallelogram or a triangle. This particular formula works for all regular polygons. So if it's a regular triangle, a regular quadrilateral, or a square, regular pentagon, etc. It works for all regular polygons. It states that the area of a regular polygon with side lengths S is half the product of the apothem, A, and the perimeter, which is capital P. So we would write that formula as the area of a regular figure equals 1/2 apothem times perimeter. Another way to think about this formula, which some people prefer, is to say that A is 1/2 A, the apothem, times the number of sides times the side length. So these two formulas can be used interchangeably. You basically just have to decide which one you prefer. I personally use this formula, and A, keep in mind, is the length of the apothem, not opossum, but apothem, and P is the perimeter of the polygon. Now if you noticed, a quick reminder, the apothem goes from the center point of the polygon and makes a perpendicular bisector to any one of the sides. So I really could draw in several apothems to each of these, but what we're going to do is just focus on one of the triangles when we work with our area. Alright, let's look at example 2. Example 2 says find the area of a regular polygon. A wooden coaster is a regular octagon with 3 centimeter length sides and a radius of about 3.92 centimeters. What is the area of the coaster? So since this is a regular octagon, we know all of the side lengths are going to be 3 centimeters. We also know all of the radii will be congruent, and that's 3.92 centimeters. Now they gave us the picture, which was really helpful. The one thing you want to be careful of is the radius. This, for example, that I just drew in, we'll call that T. RT is not a radius because a radius has to go from the center point to a vertex, and T is not a vertex. So keep in mind when you're talking about a radius, if you had to draw your own picture, you would want to make sure you're going to the vertex, not to the midpoint of the side. So we know these measurements. We need to find the area. Well, anytime we're dealing with a regular polygon, we're going to use the formula A equals 1/2 the apothem times the perimeter. Now, up until this point, a lot of our area problems were pretty simple. We kind of were working with shapes we were very familiar with. This is a little bit more complex, and we are going to spend a little extra time on this target as a result. So if you're not understanding every piece of this today, that's okay. This is just an introductory. We'll continue to work on it. So our two parts that you're going to find are the apothem and the perimeter. You're going to very carefully label your work for these problems because there are a lot of steps involved. So please make sure as you're showing your work, you go ahead and include that and label what it is that you're finding. So since we need an apothem and a perimeter, we can start by finding either one of those. In my opinion, the perimeter is the easiest to find for this problem because we know that each side length is a length of 3 centimeters and there's 8 equal sides. So we could do 3 times 8 to get a total perimeter of 24. So we know the perimeter of this shape is 24 centimeters. Now our last job is to find the apothem. Well, I'm going to focus on this triangle right here. So essentially when you're dealing with these regular polygons, you're just going to choose a triangle to work with. Now, this is going to be an isosceles triangle, so each of these lengths are 3.92 since each of those are the radius. Now if I go ahead and draw on my apothem, the apothem is going to bisect the side length and make a perpendicular. So we know we've just taken that isosceles triangle and divided it into 2 right triangles. The next thing we can do is use our trig functions and Pythagorean theorem. We're going to use those once again. Well, we know each side length is a length of 3. So when I draw in the apothem, it's going to bisect that 3 centimeters into two 1.5 centimeter lengths. So essentially, if I were to take and draw that triangle, it looks something like this. Here's the 2 radii. Here's the center. Here's my apothem. And the apothem is dividing that 3 centimeters into 1.5 centimeters and 1.5 centimeters. So I just redrew the picture focusing just on the triangle. So what I want to do is, knowing the apothem makes a perpendicular with the side length, is I want to find A. So I'm going to use part of this triangle and Pythagorean theorem. So A squared plus B squared is equal to C squared. Well, my legs are the apothem and the 1.5. So A squared plus 1.5 squared is going to equal the hypotenuse squared, which in this case is 3.92. Go ahead and take a minute to find the length of A. Pause your video and do that. Okay, by using Pythagorean theorem, you should have found that the apothem is about 3.62 centimeters. If you did not come up with that, just look through my steps and see if you can find your mistake and continue on from there. So now we have the 2 important elements that we need to find the area of this regular octagon. So I'm going to use my formula, A equals 1/2 the apothem, which we found to be 3.62 approximately, times the perimeter, which we found to be 24 centimeters. And if you find the product of this, keep in mind this is not the distributive property because we don't have a sum or a difference. We're just simply multiplying. So 1/2 times 3.62 times 24 is about an area of 43.5 centimeters squared. Now, as I said, this is not the easiest process, so as we do more of these, they're going to get easier as time goes on. So just be patient with this target. Let's try one more example. Example 3 says that we're finding the area of a regular polygon. It says a regular nonagon, keep in mind that means it has 9 sides, is inscribed in a circle. It has a radius of 4 units. Find the perimeter and area of the nonagon. So our ultimate goal is to find the perimeter of this nonagon and its area. Well, let's put our information on our picture. So we know that the radius is 4 units. So keep in mind the circle and the nonagon share the center point. So I just drew that in. And then the radius, there are going to be 9 radii here. There's technically more if you were to draw them in to the circle. But for the polygon, there's 9 radii. That's going to be from going from the center of the circle to any vertex. So I could have used that, or this length, or this length, and so forth. I could draw on all of these lengths to be 4. Now, what you should really start to do after you get good at this is just focus on one triangle. So that's what I'm going to do. I'm going to focus on this triangle right here at the bottom in the center. So we know that the 2 side lengths of that triangle are 4. It's an isosceles triangle, as they all will be. So I have these 2 side lengths as a length of 4. Now, in order to find the area, I'm going to have to calculate 1/2 the apothem times the perimeter. Well, I don't know anything about this shape besides the radius, so right now I can't do a whole lot yet. So I'm going to still focus on this triangle that I have in the bottom middle, and I'm going to draw on my apothem. The apothem, keep in mind, bisects the side length, which we don't know, and it makes a perpendicular with the side length. So I've just created 2 congruent right triangles. What I need to do is start by finding some angle measures. So I'm going to start by finding the central angle, which is the angle of this entire triangle. Well, if you revisit example 1, when you're finding a central angle, it's going to equal 360 degrees, always 360 because they form a circle, divided by however many sides you have. In this case, we have 9 sides. So that central angle is 40 degrees. Now, the apothem bisects that angle. So then we have to remember to cut it in half. So each of these are 20-degree angle measures. Now we look at this, since it's a right triangle, we can use trig to find the apothem. We can't use Pythagorean theorem here because we don't have enough of the side lengths. We only have one side length. So what I'm going to do is focus on this triangle here on the right. Doesn't matter, they're both the same. And I'm going to think about, I have to reference the acute angle, so 20 degrees. I know the adjacent, and I'm finding the hypotenuse. So adjacent and hypotenuse deals with cosine. So I'm going to do cosine of 20 degrees is equal to the adjacent side length, or A, over the hypotenuse. I'm going to make that a proportion and cross multiply. Go ahead and pause your video and find that. You should have found that the apothem is 3.76 units. So now what we need to consider is we now have, from that blue triangle, it had a 20 degrees angle, a hypotenuse of 4, and now I just calculated the apothem to be 3.76. So now let's think about how we could find this last side length. Well, we can use Pythagorean theorem to find x. So that's what I'm going to do now. Go ahead and pause your video to do that. So you should find that x is about 1.36 units. The reason why we needed that is we need the side length of the entire nonagon. So if this little part where it was bisected was 1.36, we're going to double it to find the entire side length. So each side length is going to be a total of 2.73 units. The reason why that's helpful is now I can calculate the perimeter. The perimeter of this shape will be equal to 2.73 times 9 sides. So therefore the perimeter of this nonagon is going to be about 24.56 units. Now that we have the perimeter, finding the area is pretty easy. So I'm going to say that the area is equal to half the apothem. Well, we found the apothem to be 3.76 earlier. So 3.76 times the perimeter, which we just calculated to be 24.56 units. So the total area of this shape is 46.18 units squared. Go ahead and try the you try nows. We're going to spend quite a bit more time on this in class the next time we meet, and then we'll have another day to practice. So bring all your questions. I know you're probably going to have several. That's okay. We'll talk about those more as we go. Have a good day.